Hello, and thank you for watching this short presentation that summarises the application of mass spectrometry for contributing to the measurement of half-lives of radionuclides. My name is Ben Russell and I work in the nuclear metrology group at the National Physical Laboratory. I would like to thank a number of my colleagues who helped with putting this presentation together, primarily Emma Brasher, who did a lot of this work as part of her PhD. This is just to give some context of why accurate half-life measurement is so important, and it underpins a number of applications shown here, and that includes the geological dating of materials, nuclear forensics for determining the source of contamination, climate and ocean circulation studies where radionuclide measurement can be used to model past climates and then also be used for looking at future climate change scenarios as well. Nuclear medicine of critical importance for ensuring patient safety and effective treatment, radiation protection for those who work in the nuclear industry, and nuclear decommissioning and waste disposal, making sure that when waste is characterised, it is done accurately and that therefore it is disposed of via the correct waste sentencing route. In the past, long half-lives were measured using primary counting techniques alone, and mass spectrometry was not considered as a technique until perhaps the last 30 years or so. The graph on the right-hand side at the top shows the cumulative number of half-life studies over time, and you can see mass spectrometry increasingly being used. There's also a breakdown there that shows that inductively coupled plasma mass spectrometry, or ICP-MS, is the most commonly used technique, with thermal ionization mass spectrometry and accelerator mass spectrometry also being applied in some studies. As the sensitivity of mass spectrometric techniques has improved, the frequency and variety of the applications has increased, and that includes looking at half-life measurements. The chart on the lower right-hand side shows the division of ICP-MS designs used for half-life measurements, with multi-collector ICP-MS being the most commonly used technique. And as we'll show in future slides, the multiple detectors on the instrument make this a well-suited technique for half-life measurements compared to single detector instruments. This slide and the next slide aims to show how the activity and the mass of a radionuclide can be linked, and therefore why mass spectrometry can play a role in contributing to half-life measurement. Starting on the top left, the radioactive decay rate is a measure of the number of disintegrations per unit time, where n is the number of atoms. Moving down, that equation can be rearranged, where the decay constant can be related to the fraction of atoms undergoing decay per unit time. Moving over to the top right-hand side, as the number of atoms can be found from the mass of the analyte of interest, its molar mass, and Avogadro's number, the decay constant can be expressed using the equation on the top right-hand side, and the half-life can then be related back to the decay constant. So what does this ultimately mean? Well, looking at the equation at the top there, with the mass related to the activity, the molar mass, the half-life, the natural log of 2, and Avogadro's number, for an equivalent activity, the number of radioactive atoms is proportional to the molar mass and the half-life. And whilst the molar mass can vary by a couple of orders of magnitude, the half-life can of course range from seconds to millions or billions of years. The longer lived the radionuclide is, the more atoms there are to count, and mass spectrometry is therefore more sensitive for measuring long-lived radionuclides. If you take the specific activity for a given radionuclide, we take the natural log of 2 and Avogadro's number, the mass and the half-life, you can then do 1 divided by the specific activity to look at the mass equivalent of 1 becquerel. In this table it's been converted to picograms, or 1 times 10 to the minus 12 grams, and that is done because the mass spectrometry detection limit, specifically ICP-MS in this case, can be considered to be in the region of picograms per gram regardless of the detection limit that can be achieved. You can see that for strontium-90, the mass equivalent of 1 becquerel is 0.2 picograms because the half-life is around 30 years, whereas for uranium-238, which has a 4.5 billion year half-life, the same activity, 1 becquerel, has a mass equivalent of 8 times 10 to the 7 picograms. So for the same activity, there are significantly more atoms to count when measuring a long-lived radionuclide compared to a short-lived radionuclide. This slide shows a similar thing to the previous slide, just in graphical form. So you can see the half-life in years on the x-axis, and then you have the activity concentration on the left-hand y-axis and the mass concentration on the right-hand y-axis. And examples are given for several naturally occurring radionuclides. And you can see, for example, lead-210 with a half-life on the order of 20 years has got a higher activity concentration and a lower mass concentration for an equivalent activity compared to, again, something like uranium-238, which has a 4.5 billion year half-life. As mass spectrometry has improved over the years, what we're going to do is move to measure shorter and shorter half-lives, both for a range of applications and also more recently for contributing to half-life measurements. And this slide follows on from the previous one, just expanding out into the range of applications where mass spectrometry can be used. So perhaps where it all began with long-lived actinides, as I say, as mass spectrometry has improved, the number of actinides that can be measured has expanded. Medium-lived radionuclides, particularly those with half-lives on the order of several tens of years, mass spectrometry is now increasingly used for measurement of those because of the high sample throughput compared to equivalent decay counting techniques, particularly alpha spectrometry or liquid scintillation counting. Isotopic ratios is a powerful tool for determining the source of nuclear contamination, and for long-lived low abundance radionuclides that have a very weak decay signature, mass spectrometry is considered as the priority technique, or is increasingly seen in that way. To underpin all of this, radionuclide standards with the impurity and activity levels for mass spectrometry applications are increasingly sought after, and there is an ongoing drive to produce these to support these applications. As with all mass spectrometry applications for radionuclide measurement, if you are looking at using this to count the number of atoms to contribute to half-life measurement, any interferences present in your sample must be carefully considered. The examples are shown here for strontium-90. So the main ones we consider are isobars, in this case zirconium-90, polyatomics formed by reactions of gases in the plasma or potentially in the reaction cell depending on the instrument design used. So for example, yttrium hydride or nickel dioxide. And tailing, where you have a high concentration of a stable isotope at a neighbouring mass, in this case strontium-88. So what has to be considered when we're looking at using mass spectrometry for half-life measurement? Well, the second bullet point has already been covered. Any interferences must be removed using either offline chemical and or instrument-based separation, depending on the setup that you have. The mass bias is a critical thing to factor in, as we'll come on to describe, because in the case of ICP-MS, which is the focus of today as it's the most commonly used technique, lighter isotopes are more scattered than heavier isotopes, so the instrument will naturally be biased towards heavy isotopes, and that must be corrected using isotope dilution, which we'll explain in subsequent slides, and sample standard bracketing with a certified isotopic standard. The detector response must also be considered, so this calibration, this answer is given for a single collector instrument where you might have a pulse and analog mode, but it's equally important if you have multiple collectors where you need to calibrate each detector's response. And monitoring an internal standard during a run should also be considered to make sure that you factor for any changes in instrument performance during a run. This slide shows the general experimental approach towards half-life measurement, and the areas highlighted in the red boxes are where mass spectrometry has a role to play. So you have an isotope spike of a known amount, and you look at isotopic ratio analysis, and you also look at the mass of the source material. From there you go on to measure the concentration of the radionuclide, which when combined with Avogadro's constant, as described previously, you can look at the number of atoms of the isotope of interest. That then, combined with the activity of the radionuclide, can determine the decay constant, and that, along with natural log of 2 constant can determine the half-life. So this is just a slightly more detailed way of showing the relationship between activity and mass, as was shown in previous slides. In terms of the approaches used for atom counting using ICP-MS for half-life measurements, isotope dilution is the most commonly used approach, and that is measurement of the relative abundance of the radionuclide of interest using another isotope of the same element. And that relies on precise instrument calibration, as mentioned, accurately correcting for any isotopic fractionation and interferences that are present. And if any chemical separation or sample preparation is carried out, then the recovery through that process must also be very well understood. The first case we will look at is single isotope dilution, where you add a known amount of the isotope of the element of interest and measure the isotopic ratio. So you have a known amount of sample, a known amount of spike, and then you measure that mixture, and from there you have your measured isotopic ratio and also your isotopic ratio before the spike. And then using a certified isotopic standard, you can factor in the mass discrimination factor and ultimately calculate the concentration of the isotope of interest. Then also prepare a set of isotope dilution solutions that can be prepared against a reference standard, and from that you can generate a calibration curve, and that can be compared to the spiked sample to ultimately determine the composition of your sample. There are more advanced isotopic dilution techniques depending on the application and the information you have about your starting sample. So first of all, there is double isotope dilution, and you use this when the composition and the amount of the spiked solution is unknown. So reverse dilution is when the spike is diluted with a natural standard of known composition, and that's followed by dilution with the spike and the sample of interest. There is also a triple dilution, which is a double reverse isotope dilution, and that eliminates the need to determine the sample composition. Now, this theoretically lowers the measurement uncertainty, but it does potentially lead to a longer procedural time, and the triple dilution approach is recommended for enriched spikes with challenging sample compositions or when there's memory effects between sample dilution stages. This slide shows a specific example of isotope dilution mass spectrometry, looking at counting the number of atoms of uranium-238 using uranium-234 dilution. And the equation at the top there shows everything that has to be considered for both the mixture, the sample, and the spike, respectively. And from that, the half-life can be calculated using the equation on the bottom half of the slide, and that contains information, all of which has been covered in previous slides already. Now, one thing that you may have spotted with that specific example is that you're using a radioactive isotope, uranium-234, for dilution to measure the half-life of another radioactive isotope, uranium-238. Now, in some cases, the radionuclide of interest has got stable isotopes that can be used for dilution. For example, zirconium-93 has a number of stable zirconium isotopes, or samarium-151 has even more options for stable samarium isotopes. But in some cases, and there's some examples shown in the table on the right hand side, there are a number of particularly actinides where there is no stable isotope that can be used for dilution. So there is another option in some cases, which is separation and ingrowth, and that is where you look at a measurement of a long-lived radionuclide with a relatively short-lived daughter radionuclide. This requires chemical separation followed by ingrowth measurement relative to the parent radionuclide over several years. So it is a long-term measurement, but it does eliminate that issue of using a radioactive isotope as a dilution. It assumes there is no external input of either radionuclide over time, but on the right hand side there, the graph shows an example there for thorium-230, uranium-234 amount ratio over a period of around 3 to 4 years. And some candidates are shown in the table there where it's possible to look at this approach for half-life measurement. So again, here is a specific example. This time looking at uranium-234 half-life measurement through thorium-230 ingrowth. So the ingrowth after separation can be calculated using the equation on the left-hand side, where you factor in the number of atoms as a function per unit time, the decay constant of the two radionuclides, the thorium-230 content after chemical separation, where the time is 0, where effectively the clock starts, and the elapsed time since that separation took place. The low decay constant and the short ingrowth time of several years means the decay constant time is close to 0, and using a couple of approximations and the decay of the accumulation of thorium-230 and uranium-234 decay is negligible, you determine the number of atoms of uranium-234 at the time of separation, and that the number of thorium-230 to uranium-234 atoms is linearly proportional to the time since separation, where the regression coefficient is equal to the decay constant. So this is just saying that whilst isotope dilution mass spectrometry is the most commonly used approach, the ingrowth method can be considered for certain radionuclides as some advantages over isotope dilution for specific cases, but you'd have to factor in that a measurement time of several years is required. The next two slides show a summary of half-life measurements that have been made where mass spectrometry has contributed through atom counting. There are a range of radionuclides used. There's also information on the sample that was used for the measurement, the preparations that were made, including any chemical separation, the primary counting technique that was used to determine the activity, the mass spectrometry technique used, and the half-life and the uncertainty value that came with it. The reference in each case is also provided. And this is a second slide summarizing half-life measurements where mass spectrometry has been used. And this is the end of this presentation on the use of mass spectrometry for contributing to half-life measurements of radionuclides. I hope that you enjoyed it, and thank you very much for your attention. If you have any questions, please do get in touch. Thank you.